Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 chemistry students. Welcome back. I hope you're fine and still healthy. Alan is my name, still with you in chemistry lessons. So we are on our topic of electrochemistry, and that is unit 17, which is about reduction and oxidation reactions. Today we are heading into lesson 5, as you can see, which is on balancing redox reactions in aqueous solutions. Aqueous implying water, but of course we shall see a few of the conditions that are involved in. So briefly, where we are, we've looked, or we started with the defining oxidation and the reduction, then we combined to bring into the redox reaction, which is oxidation reaction and the reduction reaction. When they are combined, it becomes a redox reaction. Then we went ahead to look at the oxidation numbers. Then we're now going to combine everything that we've already looked at in reduction and oxidation reactions as we finalize up this unit with balancing redox reactions. So quickly, what we're going to look at in this lesson will be applying the half reaction method in balancing redox reactions. I always give you the aspects or the key components of the lesson for you not to miss up. So we're going to be using much more of the change in oxidation states and looking in details about the reaction conditions. Is it in neutral solution? Is it in acidic solution? Is it in basic solution? The reaction condition will tell us what to do when we are balancing the redox reaction. But the method to use is half reaction equation method. So, and as usual, I always highlight the lesson objectives. We have two objectives to work on. One is to identify and balance half reaction equations for each reaction. When I talk of half reaction, you understand we're looking at oxidation half side and reduction half side. Then when we balance those half sides, then we can connect them to bring about the redox. So the first objective is to identify, then we balance each separate. The second is to combine, deduce a balanced redox reaction from the half equations. So that is what we're going to look at in today's lesson. Let's make a quick highlight of what we looked at in the previous lessons, which is about oxidation numbers. As you noticed, it is one of the key aspects. So we're going to be using it as we derive, or as we formulate, or as we come up with which species is undergoing oxidation and which species is undergoing reduction. So these are the guidelines we looked at in details and performed calculations, but for the case of today's lesson, I'm bringing them for a quick review, which will be helpful. Group 1 elements and group 2 will always have oxidation number as +1 and +2 respectively. Hydrogen will always assume a +1 provided it is bonded to any other nonmetal, but a -1 provided it is bonded to metals, mostly in the metal hydrides. Then oxygen always is usually having -2, but with a few exceptionalities in peroxides, superoxides, and when it is bonded to fluorine. You know the reason why, because fluorine is more electronegative than oxygen. So it will tend to pull electrons from oxygen, making oxygen to exhibit a less negative oxidation number, or it will not be exhibiting -2. Its usual number. Lastly, Fluorine will always have a -1 because it is the most electronegative element, so there is no any other atom of an element that can take electrons from fluorine. That's why there is that word always. Whenever it is in any compound, it will always have that -1. So that is the summary of what we looked at in details. I still implore to any student who missed our previous 4 lessons, please, I encourage you to check for them online, and that is the e-learning for REB, and you will catch up with them. So let's now go to today's work. So that is activity 1. Activity 1, use the half reaction method and balance the following equations under specified conditions. Use the half reaction method and balance the following equations under specified conditions. Part A, no conditions. That indicates it is in a neutral solution because the conditions are, as you can see, take a look on the slide. Because here, as we are not identified, or we've not identified the condition to be acidic or media, that implies it is in neutral. Then for B and C, that is in acidic media. For D and E, that is in basic medium, meaning we have OH for basic, meaning we have hydrogen ions for acid. So we are going to use the half reaction method. Before we get started on this activity, I want to show you the guidelines involved in the half reaction method. I will not read the whole of them, but as we do the exercise, you will really understand what all these guidelines and how they come about. So let's get started. Let's get started on our activity 1. We are starting with part A. Let's go through it together. Part A, which is tin 2 ions reacting with iron 3 to form tin 4 ions, then plus iron 2. Now, this is our first number we are to deal with. I'm going to be switching, taking you to the guidelines. So as I go through the number, I want you to read through the guidelines for you to really understand them. There is no need for me to reread them when we can actually see them. So, having this as our activity 1, the first guideline is identify and separate species undergoing oxidation and species undergoing reduction. How do we know a species is undergoing oxidation, and how do we know a species is undergoing reduction? So what we do is we look at the changes in oxidation numbers. We're talking of how do you know the species which is undergoing oxidation and reduction. You look at the changes in oxidation numbers. Let's consider tin. Remember the principles of oxidation states. The charge, if it is ionic compound or if it is charged, the charge becomes the oxidation state. In this case, we have +2 to +4, indicating for tin there is an increase in oxidation number, meaning this underwent oxidation because we moved from +2 to +4. If you look at iron, it moved from +3 to +2. What does that imply? There was gain of electrons, so we have reduction in here. because it gained electrons. Here we have oxidation because it lost electrons. So after us identifying that, then we can now go ahead and write the half equations. What is, in this case, we are going to take the oxidation half equation. The oxidation side, which is tin 2 going to tin 4, and aqueous. So, first rule is, after you've identified the reduction and oxidation, balance the atoms. If there is no oxygen, it's okay. If there is oxygen, balance other atoms, then oxygen and hydrogen at the end. As you can see, we do not have any other atom, so we shall directly go to electrons. Positive 2, positive 4. Oxidation electrons are written on the right-hand side. So to balance the charges, this involves 2 electrons. Positive 2 plus minus 2, we get positive 2. No, positive 4 plus minus 2, we get positive 2 and positive 2. So the oxidation side is balanced. Let's go to the reduction side. On the side of the reduction, we have iron 3 cations forming iron 2 cations in aqueous. So, balancing the charges, positive 2, positive 3, positive 2. Remember, reduction electrons are gained. So we add electrons on this side. So, if we add 1 electron, it balances up. And from the principles, the electrons lost is equal to the electrons gained. So in this case, we need 2 multiplied by 2 to balance up the electrons. Electrons lost equal to electrons gained. So to get the overall, we shall add these 2 reactions together. So we have tin 2 plus, then 2 iron 3 aqueous. This is giving us tin 4 in aqueous state, then plus 2 iron 2 in aqueous state. So this is our first balanced equation. Now, this was in a neutral case. There is no acidic or basic component in the solution. So if we had to look at where we have acid and a basic component, how to balance them differs from how we came up with this. So let's directly go back a little bit to our X activity. Let's go back a little bit to our activity and do part B. That was part A. So let's go to part B. Best I make a line here to separate these components very fast. Good. So part B is the dichromate plus iodide aqueous going to the chromium 3 plus iodate iron aqueous. But this is clearly indicated it is in acidic solution. In other words, there are hydrogen ions in this component. As usual, we must determine which species is undergoing oxidation and which species is undergoing reduction by looking at the oxidation numbers. If I look at this, this is -1, and in here I have to calculate. Do not assume, calculate. How do I calculate? From our principles, I will call this X. plus oxygen, I give it -2 since it is more electronegative than iodine, but there are 3 oxygen atoms equaling to -1, the charge. So you'd end up having X here becoming +5 by calculation. So our I is +5 by oxidation state. Do the same thing. Here you can see it is directly +3. We don't need to calculate. When you calculate here, do the same calculation like as we've done here. You'll end up having 2x, x for chromium times 2, plus -2 times 7, giving us -2. So you'll end up having x as +6. A quick calculation. This is 14, take it here, becomes +12 divided by 2, giving you 16. So this is giving us +6. So you notice now chromium changed from +6 to +3. Iodine changed from -1 to +5. So we can tell which species is undergoing oxidation. Oxidation side. I did this to show you how to come up with the oxidation numbers, but you already know how to do it. In an exercise, you may not need to do this. It is not really needed. This is for you as you do practice. So oxidation, we are noticing this is undergoing oxidation. The I minus aqueous going to iodate aqueous. Now, it is at this moment that we apply our principle. Look at guideline number 2. If you have a case of this category, balance other atoms other than oxygen. We notice all other atoms are balanced, right? So, to balance oxygen, add water. Water will bring in will bring in oxygen. In this case, we add 3 water as a liquid. So, 3 oxygen is now balanced. This side is 3, this side is 3. But we've brought in the aspect of hydrogen. To counteract hydrogen, we need to add hydrogen the other side. So this is 6 hydrogen ions. So we have oxygen, iodine, and hydrogen all balanced, but the charge is not balanced. This is -1. Here we have -1 plus +6, which gives us +5. So to get -1 balanced, we need to add 6 electrons. In this case, the charges will all be balanced. That is for oxidation. Let's quickly look at reduction side. Reduction, which is involving the dichromate. So the dichromate is going to chromium 3. I think you must be noticing, I'm leaving the gap for me to add the other components. I'm leaving the gap to add the other components together. So, what do we notice? Chromium, the first aspect is to balance other atoms other than oxygen. We have chromium, we can balance it by putting a 2 here. All right, we remain with oxygen, it is not balanced. So to balance oxygen, we use water. I would add 7 molecules of water. You notice adding 7 molecules of water has brought in hydrogen ions. So we add 14 hydrogen ions on this side. 14, this is 7 times 2. So our hydrogen is balanced, our oxygen is balanced, our chromium is balanced, but the charge, which is number 2, part D on the guidelines, the charge is not balanced. So how do we balance the charge? Count. -2 plus positive 14, which becomes positive 12 this side. But here we have positive 6. Remember, reduction, electrons are added on the left side. So we can balance the charge by adding 6 electrons. When we add 6 electrons, which are negative, plus positive 14, it will become, no, this is already positive 12, plus minus 6 will remain with positive 6, which is 2 times 3, which is positive 6. Charges are balanced, our atoms are balanced. So we have balanced oxidation side, balanced reduction side. The next thing is now to get our overall. The overall redox reaction will be adding this and this. When you look closely, the electrons are balanced, right? Yes, 6 here and 6 there. So we simply add this part and this part. So we shall have the dichromate minus aqueous plus our iodine aqueous. Now, the trick comes in here. You notice we have water here. We have water. So what do? For water, okay, let's first handle hydrogen. It's here. We have hydrogen here and hydrogen here. So because this is more than this amount, this is 14, this is 6, we are going to bring this hydrogen this side, and when we cross the arrow, it changes the sign. So it will be 14 minus 6, which gives us 8 hydrogen ions. Bring this to here. It becomes a negative because it has crossed our arrow sign. Then the water. This is lower than this. We take this side and subtract it from there, but it will now become a product. So our main component making up the reactants are done. Remember, electrons have gone. Electrons lost must be equal to the electrons gained in here. Finally, we have our product as 2 chromium 3 ions plus the iodate ion, then plus 7 minus 3, giving us 4 waters. So can we check if everything is balanced? Hydrogen is balanced. Oxygen is balanced, 3 plus 4, 7, and the charges. And so this becomes our aspect with acidic solutions. Let's conclude up with another example, which is basic. When we are doing the basic, that is part D. Let me quickly do D. Manganate ion plus iodine, giving us manganese 2, then plus iodine, aqueous. Remember they are aqueous, but in this case, this is in basic, indicating we have OH. Quickly, I will not do the calculation, but it is the same. Here, this is in positive 7, manganese. This is in positive 4. Minus 1, and this is a 0. Here, it will have lost electron, will have gained electron. I will quickly go to oxidation side. I've already seen my oxidation side by looking at the oxidation states. So oxidation side, here I have I minus going to iodine in aqueous state. So first principle, balance atoms. I balance them by putting a 2. Balancing atoms brings difference in charge. So I will balance the charge by putting a 2 there. That is oxidation done. Very fast. Now, let's go to reduction. Remember, in this case, we have basic. In the reduction, what do we have? We have permanganate going to manganese 4 oxide. So, what do we do? Balance atoms. Balanced manganese is balanced. We balance oxygen. Balancing oxygen, we need to add water here. 2 water. So, by putting water there, oxygen is balanced, but hydrogen is not. We need to put 4 hydrogen ions here to balance hydrogen atoms. So remember, it is in basic condition, and that is the only trick I want you to take notice. Look on the slide. The only trick in here is in basic conditions, after balancing your hydrogen ions, add the same amount of OH ions on both sides. Add OH ions on both sides. When that is done, you notice this will become water. Hydrogen ions and OH forming water, but this case will remain with OH ion. And that is the main trick that distinguishes basic from acidic. Next, balance the electrons as usual. Balancing the electrons, this is, remember, positive 7 here. We can quickly look at this is minus 4. So to balance up, we need to add 3 electrons to balance up the charge. Minus 1 plus minus 3 becomes minus 4. So that is well balanced. Overall, as I conclude, the overall will be adding both sides. Please go on and find the overall equation by multiplying by 3 here, multiply by 2. You will find up the overall equation. Do that. At this moment, you already know the crucial part, which was that. Find it, and that is it. As usual, I would like to leave you with that assignment. Please attempt it and stay safe. Bye.